Dragos Kiriak. I'm this year's QGEM co-director for 2016. I'm here joined by Kersh. Kersh used to be Kersh was a former alumnus of QGEM 2016, and now he's pursuing his PhD at Berkeley. We're going to have a short interview. We're going to talk about some of the important synthetic biology questions. So Kersh, tell me a little bit about some of the people or events that influenced you to be where you are today. So PhD at Berkeley, in synthetic biology, preferably, like what specifically do you have, who's your PI currently?
Right now I work for Michelle Chang.
Okay.
She's a PI who focuses on both metabolic engineering and in vitro biochemistry. She takes a bit of a synthetic biology approach to some of her questions, but not all.
Okay.
Mainly it's looking at trying to make polypeptides, which are used as a form of antibiotic in our case, and also she's working on making biofuels. And my particular project looks at carbon dioxide fixation and how to use CO2 fixation for the ultimate production of butanol. So going from solar panels to our organism, which feeds on the products of solar panels and CO2, and using both of those things to make butanol, which is an alternative fuel that we could use for our cars while we're still stuck in the age of using internal combustion engines.
Okay. For example, you mentioned that your idea of taking the products of solar panels and then turning it into butanol. Are you familiar with some of Pam Silver's work from the Weiss Institute? I believe she's working on synthetic leaves right now.
Yeah, so actually Pam Silver and Dan Nocera have looked into exactly what you're talking about. Sort of, they call it I believe they call it the bionic leaf or something like that. And the idea there is similar to what I'm talking about, where they go from a light that produces the essential photocurrent required for essentially getting these organisms that they're interested in to make hydrogen fuels.
Yeah.
And so their goal is to make hydrogen fuels from electrodes, using the organisms and the beautiful innate capacity of biological enzymes to carry out reactions. And so that's what they're going after. Our project is a little bit different because when we're trying to make our products, we're looking at a sort of intermediate between going from light to product, and that is a chemical catalyst that produces hydrogen for us. Actually, chemical catalysts are available out there to produce hydrogen. This isn't a new thing, but what's very new is actually using our organisms to actually consume hydrogen and consume CO2 to make our ultimate fuels. Because we personally do not believe that hydrogen is going to be the next fuel for the next economy. We believe that hydrogen is going to be an intermediate for the fuels of the next economy.
I guess some of the next questions would be, why did you decide to go into synthetic biology, and how did QGEM influence that decision?
Yeah, that's a great question. It's hard to pinpoint an individual experience that suddenly, resulted in enlightenment.
Okay, yeah.
But I think that there were a couple people, a couple events that really tuned me in to what was going on. For instance, I took a course here at Queen's called Biochem 218, and when I was an undergrad second year, I was not very interested in a lot of the scientific subjects I was learning. I felt like a little bit disenfranchised from the process of life sciences at the time because people were really focused on getting into medicine. That wasn't me.
Yeah.
But I found in Biochem 218, this basic biochemistry course, an understanding of what biology is that transcended what the other courses were offering. It wasn't just a list of facts. It was a real granular understanding of what was going on at the genetic level, at the transcriptional level, what was happening at the level of protein-DNA interactions, protein-protein interactions, these quantifiable, measurements that you can make that are the basics of our human cells, of prokaryotes, of other organisms. And to me, it amazed me because I thought this is where true knowledge is being produced. And if you look at medicine, a lot of the discoveries in molecular biology are the fundamental knowledge set for what's happening in medicine now. Molecular medicine, what is that even? A lot of that is basically molecular biology. And so I was tuned into molecular biology first as a science. I was interested in going to graduate school for molecular biology as a science. But what tuned me in to the potential for the technologies that are being used in molecular biology for the science and potential use of those for commercial purposes was my own experience working and making my own businesses, my own experience with QGEM, which is sort of run in a similar way to a business, and also some of my experiences at local conferences in Toronto, where I saw biotech founders who had not only a sense of appreciation for the science of molecular biology, but also a sense of what was to come. And I felt like if I was doing it in business, I could do it so much faster and so much better than if I was working in academia. And so combined with my interest in molecular biology, I realized that for me, it was a matter of commercialization that was important, and actually taking what I was learning in that class and applying it at a quick level, at an unprecedented global level. And I think like that kind of impact you can really make in the way that I'm describing if you start your own business. And I realized going to Berkeley would be one of the stepping stones along the way, because not only did it provide me with the understanding of molecular biology that I was looking for and give me an opportunity to further that understanding, but there are a lot of researchers at Berkeley that are interested in this sort of fusion concept of synthetic biology, which is using the technologies of molecular biology with the problems in health and environment, and potentially considering the modular aspect of genetic components and combining these into potentially commercially viable products. And I think that was where I was spellbound. I realized we're seriously entering the golden age of biosciences. We are at an unprecedented time, and it's not so much that there are too few tools to answer the kinds of questions we want, but that we have so many tools and we need to decide which ones to apply to the problems that we have. And so that's what I'm really excited about, because suddenly we're spoiled with technology and we need to decide how to use it.
Yeah, I guess, some say if all you have is a hammer, every single problem looks like a nail. Mm-hmm. Right? But now we're spoiled with all these different tools. So for example, we have CRISPR-Cas. Supposedly there's a new sort of gene editing sequence platform called Argonaut proteins that are getting some publicity. What are some of the most important tools, in your opinion, right now in synthetic biology?
Yeah, that's a great question. I think besides the use of Cas9 and restriction enzymes and high throughput robotics, the most exciting thing to me is microfluidics.
Okay.
Is the ability to carry out an experiment not once per second like you can with the robotics and 384 well plates, but 2,000 per second. We're not measuring experiments in terms of how many days things will take. We're measuring experiments in terms of kilohertz. How many can
experiments
per second?
Yeah.
And I'm currently working on experiments at the scale of 10 to the 8 in 3 to 5 days. And that is what synthetic biology needs, because the problem is it takes a long time to complete the cycle of design, build, and test, right? And analyze and learn.
Of course.
That cycle takes time, right? For us, as we start off in QGEM and we're learning the basics of like what does this mean, and we're reaching for really ambitious and interesting goals. The realization I think most of us come to is that synthetic biology takes a long time.
Yeah, of course.
Right? And one of the key principles of a lean startup is that you're able to create a very tight feedback loop, right?
Yeah.
So in lean startup talk, you're basically trying to go from, it's essentially design, build, test. You have a hypothesis, you have a sort of leap of faith that you make in terms of what you think your customers want. You try it out, you see from the feedback that the customers give you whether or not it's a good product or not. Use that information to design your next one. You iterate, you iterate, you iterate, you iterate. Someone who programs knows what it means to iterate constantly until you get a program that works the way you want it to. and there's tons of ways that things can get bugs. But what if it took you 4 months to try one program source code, right? It would be ridiculous.
Yeah.
It would take forever to debug. It would take a long time to actually figure out, excuse me. It would take a long time to actually figure out where the problem is and then actually take time to redo it and potentially fail again. And that's kind of what synthetic biology is like right now. You have people who spend a lot of time, a lot of months trying to do one thing, right? And they might do it they might try 10,000 variants, 100,000 variants of a protein of interest or an enzyme of interest, and they want to get that enzyme of interest doing something important. But that scale is not enough. That scale is not close to enough for the kinds of possibilities that biology gives us. And so given those possibilities, if we want to create a system or a protein or a genetic computational platform, whatever you want to do, all those things require you to get through the loop very, very quickly. And I think what microfluidics does is it gives you the opportunity to get through that loop very, very quickly. I think that's going to be the secret sauce for the next generation.
For the next generation of synthetic biologists. So we talked a little bit about your research. I'm sort of wondering right now, what do you see yourself doing in the future? So do you see yourself working on microfluidics? Or you also mentioned that you want to start up, well, you're very interested in the startup culture and starting up a business. So do you think you're going to go and try and start off your own biotech company, or is it too early to tell?
I think it's still too early to tell. I think I'm still sort of learning the ropes with a lot of things, and a startup may be in the cards in my future. It might not be, but I think ultimately I'm trying to figure out what is going on in this rapidly developing, rapidly blossoming field. And it's really exciting, and I'm just trying to stick with it and see where the opportunities are. If they lead me into building my own company, great. If not, then I'll try to find another opportunity that fits my needs.
So you mentioned before that synthetic biology is rapidly expanding. How do you think that government or other authorities are sort of keeping up and keeping synthetic biology in check? And do you think what they're doing so far is enough?
I think governments are a little slow on this particular field. It's growing in sort of multiple directions, and it's hard to tell where things will end up. The government has, placed severe restrictions, at least in the U.S., on genetically modifying any kind of organism for use in the environment outside of some genetically modified foods, right?
Yeah.
The concern there is that when you create blanket bans on products, you risk the possibility of preventing truly remarkable and well-designed systems and products from coming out to the market that could be safe and could be well-regulated. And I think ultimately what might happen is synthetic biology, as we talk about it, will become more easy to define.
Yeah.
The government will be more willing to set nuanced regulation on what should and should not be allowed. I think this is a truly scary time in some ways for regulation agencies, because it's very difficult to see what's going to happen before these scientists and engineers even see it. And so I think the best thing that can be done is that a dialogue ought to be created between government officials and between small startups and larger organizations and universities to try to figure out what the middle ground is that is allowing us to safely genetically engineer organisms and also engineer them at a pace that really matches our potential and our need. So there's definitely more to come. I think the government's been a little slow on this.
Yeah. Okay. Thank you.